How do nuclear weapons work? Modern nuclear weapons work by combining chemical explosives, nuclear fission, and nuclear fusion. The explosives compress nuclear material, causing fission. The fission releases massive amounts of energy in the form of X-rays, which create the high temperature and pressure needed to ignite the fusion. All matter is composed of atoms, incredibly small structures that house different combinations of three particles, known as protons, neutrons, and electrons. At the center of each atom is a nucleus, where neutrons, protons are bound in close proximity together. Most nuclei are relatively stable, meaning the makeup of their neutrons and protons is comparatively static and unchanging. During fission, the nuclei of certain heavy atoms split into smaller, lighter nuclei, releasing excess energy in the process. This can sometimes occur spontaneously, but can also, in certain instability in fission, nuclei, be induced from outside. A neutron is shot at the nucleus and is absorbed, causing instability in fission. In some elements, such as certain isotopes of uranium and plutonium, the fission process also releases excess neutrons, which can trigger a chain reaction if they're absorbed by the atoms. Fusion works in reverse. When exposed to extremely high temperatures and pressure, some lightweight nuclei can fuse together to form heavier nuclei, releasing energy in the process. In modern nuclear weapons, which use both fission and fusion, a single warhead can release more explosive energy in a fraction of a second than all of the weapons used in World War II combined, including Fat Man and Little Boy, the two atom bombs dropped on Japan. All nuclear weapons use fission to generate an explosion. Little Boy, the first nuclear weapon ever used during wartime, worked by shooting a hollow uranium-235 cylinder at a target plug of the same material. Each piece by itself was not enough to constitute a critical mass, the minimum of nuclear material needed to maintain fission. But by colliding the pieces, critical mass was reached and a fission chain reaction occurred. In fusion weapons, also called thermonuclear or hydrogen weapons, the energy from a initial fission explosion is used to fuse hydrogen isotopes together. The energy released by the weapons create a fireball that reaches several tens of millions of degrees temperatures, some temperatures in the same range as the center of the sun, which also runs on fusion. This is a picture of a warhead. You've got your chemical explosive around the outside. You've got your plutonium pit right here. You've got a boost gas of tritium. Here you have your uranium outer and your fusion fuel. You have your uranium inner layer right here. This is your neutron generator. Fission primary and fission secondary are here and here. This is a diagram of a thermonuclear warhead. The explosions used in thermonuclear warheads are often described as primary, the chemical and fission explosions, and secondary, the subsequent fusion blast. However, the actual mechanisms are considerably more complicated. For example, a pure fission primary is inefficient. The plutonium pit will blow itself apart before most of plutonium-239 can fission. Instead, the reaction can be boosted by including hydrogen gas, consisting of isotopes of deuterium and tritium, in the center of a hollow pit. As the surrounding plutonium fissions, the hydrogen gas undergoes fusion, releasing neutrons, inducing additional fission. Similarly, the secondary doesn't consist purely of fusion fuel layered within Layered within it is a fusion spark plug, consisting of either plutonium-239 or uranium-235. As the primary explosion compresses the fuel from outside, the spark plug material becomes supercritical and fissions, heating the hydrogen from the inside and facilitating further fusion reactions. Thermonuclear weapons that don't include this uranium blanket are called neutron bombs, as the neutrons freed by fusion are released from the weapon. Neutron bombs therefore create a larger amount of radiation than a normal weapon of the same yield. During the Cold War, such weapons were considered for use against tank attacks and the goal of disabling tank crews without having to physically destroy the tank. These are nuclear centrifuges. Sometimes you have to have over 60,000 of them to be able to work in a nuclear plant. Uranium is found throughout the world and can be mined from mineral deposits. It can also be extracted from seawater, but doing so is currently much more expensive. However, only a small fraction, less than 1%, of naturally occurring uranium is uranium-235. Producing usable uranium requires a process of enrichment in which different uranium isotopes are separated and concentrated. Usually using centrifuges, which operate like salad spinners, this is extremely costly, difficult, and time-consuming, and is one of the central barriers to constructing a nuclear bomb. Plutonium can also be used, but only occurs naturally in trace amounts. It can, however, be produced as a fission byproduct in nuclear reactors, then separated by a process called reprocessing. Plutonium separation is easier than uranium enrichment. It involves separating different elements, not different isotopes of the same element, but it is a highly radioactive process that requires heavily shielded facilities with remote handling equipment.